An electrical insulator is a material whose internal electric charges do not flow freely, and therefore make it nearly impossible to conduct an electric current under the influence of an electric field. This contrasts with other materials, semiconductors and conductors, which conduct electric current more easily. The property that distinguishes an insulator is its resistivity. Insulators have higher resistivity than semiconductors or conductors. A perfect insulator does not exist, because even insulators contain small numbers of mobile charges which can carry current. In addition, all insulators become electrically conductive when a sufficiently large voltage is applied that the electric field tears electrons away from the atoms. This is known as the breakdown voltage of an insulator. Some materials such as glass, paper and Teflon, which have high resistivity, are very good electrical insulators. A much larger class of materials, even though they may have lower bulk resistivity, are still good enough to prevent significant current from flowing at normally used voltages, and thus are employed as insulation for electrical wiring and cables. Examples include rubber-like polymers and most plastics. Insulators are used in electrical equipment to support and separate electrical conductors without allowing current through themselves. An insulating material used in bulk to wrap electrical cables or other equipment is called insulation. The term insulator is also used more specifically to refer to insulating supports used to attach electric power distribution or transmission lines to utility poles and transmission towers. They support the weight of the suspended wires without allowing the current to flow through the tower to ground. Physics of conduction in solids. Electrical insulation is the absence of electrical conduction. Electronic band theory says that a charge flows if states are available into which electrons can be excited. This allows electrons to gain energy and thereby move through a conductor such as a metal. If no such states are available, the material is an insulator. Most insulators have a large band gap. This occurs because the valence band containing the highest energy electrons is full, and a large energy gap separates this band from the next band above it. There is always some voltage that gives electrons enough energy to be excited into this band. Once this voltage is exceeded, the material ceases being an insulator, and charge begins to pass through it. However, it is usually accompanied by physical or chemical changes that permanently degrade the material's insulating properties. Materials that lack electron conduction are insulators if they lack other mobile charges as well. For example, if a liquid or gas contains ions, then the ions can be made to flow as an electric current, and the material is a conductor. Electrolytes and plasmas contain ions and act as conductors whether or not electron flow is involved. Breakdown. When subjected to a high enough voltage, insulators suffer from the phenomenon of electrical breakdown. When the electric field applied across an insulating substance exceeds in any location the threshold breakdown field for that substance, the insulator suddenly becomes a conductor, causing a large increase in current, an electric arc, through the substance. Electrical breakdown occurs when the electric field in the material is strong enough to accelerate free charge carriers to a high enough velocity to knock electrons from atoms when they strike them, ionizing the atoms. These freed electrons and ions are in turn accelerated and strike other atoms, creating more charge carriers. In a chain reaction, rapidly the insulator becomes filled with mobile charge carriers, and its resistance drops to a low level. In a solid, the breakdown voltage is proportional to the band gap energy. The air in a region around a high-voltage conductor can break down and ionize without a catastrophic increase in current. This is called corona discharge. However, if the region of air breakdown extends to another conductor at a different voltage, it creates a conductive path between them, and a large current flows through the air, creating an electric arc. Even a vacuum can suffer a sort of breakdown, but in this case the breakdown or vacuum arc involves charges ejected from the surface of metal electrodes rather than produced by the vacuum itself. In case of some insulators, the conduction may take place at a very high temperature, as then the energy acquired by the valence electrons is sufficient to take them into conduction band. Uses. A very flexible coating of an insulator is often applied to electric wire and cable. This is called insulated wire. Since air is an insulator, in principle no other substance is needed to keep power where it should be. High-voltage power lines commonly use just air, since a solid coating is impractical. However, wires that touch each other produce cross-connections, short circuits, and fire hazards. In coaxial cable, the center conductor must be supported exactly in the middle of the hollow shield in order to prevent M-wave reflections. Finally, wires that expose voltages higher than 60 V can cause human shock and electrocution hazards. Insulating coatings help to prevent all of these problems. Some wires have a mechanical covering with no voltage rating, e.g., service drop, welding, doorbell, thermostat wire. An insulated wire or cable has a voltage rating and a maximum conductor temperature rating. It may not have an ampacity rating, since this is dependent upon the surrounding environment. In electronic systems, printed circuit boards are made from epoxy plastic and fiberglass. The non-conductive boards support layers of copper foil conductors. In electronic devices, the tiny and delicate active components are embedded within non-conductive epoxy or phenolic plastics, or within baked glass or ceramic coatings. In microelectronic components such as transistors and ICs, the silicon material is normally a conductor because of doping, but it can easily be selectively transformed into a good insulator by the application of heat and oxygen. Oxidized silicon is quartz, i.e., silicon dioxide, the primary component of glass. In high-voltage systems containing transformers and capacitors, liquid insulator oil is the typical method used for preventing arcs. The oil replaces air in spaces that must support significant voltage without electrical breakdown. Other high-voltage system insulation materials include ceramic or glass wire holders, gas, vacuum, and simply placing wires far enough apart to use air as insulation. Telegraph and power transmission insulators. Overhead conductors for high-voltage electric power transmission are bare, and are insulated by the surrounding air. Conductors for lower voltages in distribution may have some insulation but are often bare as well. Insulating supports called insulators are required at the points where they are supported by utility poles or transmission towers. Insulators are also required where the wire enters buildings or electrical devices, such as transformers or circuit breakers, to insulate the wire from the case. These hollow insulators with a conductor inside them are called bushings. Material insulators used for high-voltage power transmission are made from glass, porcelain or composite polymer materials. Porcelain insulators are made from clay, quartz or alumina and feldspar, and are covered with a smooth glaze to shed water. Insulators made from porcelain rich in alumina are used where high mechanical strength is a criterion. Porcelain has a dielectric strength of about 4 to 10 kV per millimeter. Glass has a higher dielectric strength, but it attracts condensation, and the thick irregular shapes needed for insulators are difficult to cast without internal strains. Some insulator manufacturers stopped making glass insulators in the late 1960s, switching to ceramic materials. Recently, some electric utilities have begun converting to polymer composite materials for some types of insulators. These are typically composed of a central rod made of fiber-reinforced plastic and an outer weathershed made of silicone rubber or ethylene propylene monomer rubber. Composite insulators are less costly, lighter in weight, and have excellent hydrophobic capability. This combination makes them ideal for service in polluted areas. However, these materials do not yet have the long-term proven service life of glass and porcelain. Design. The electrical breakdown of an insulator due to excessive voltage can occur in one of two ways. A puncture arc is a breakdown and conduction of the material of the insulator, causing an electric arc through the interior of the insulator. The heat resulting from the arc usually damages the insulator irreparably. Puncture voltage is the voltage across the insulator that causes a puncture arc. A flashover arc is a breakdown and conduction of the air around or along the surface of the insulator, causing an arc along the outside of the insulator. They are usually designed to withstand this without damage. Flashover voltage is the voltage that causes a flashover arc. Most high-voltage insulators are designed with a lower flashover voltage than puncture voltage, so they flash over before they puncture, to avoid damage. Dirt, pollution, salt, and particularly water on the surface of a high-voltage insulator can create a conductive path across it, causing leakage currents and flashovers. The flashover voltage can be reduced by more than 50% when the insulator is wet. High-voltage insulators for outdoor use are shaped to maximize the length of the leakage path along the surface from one end to the other, called the creepage length, to minimize these leakage currents. To accomplish this, the surface is molded into a series of corrugations or concentric disc shapes. These usually include one or more sheds, downward-facing cup-shaped surfaces that act as umbrellas to ensure that the part of the surface leakage path under the cup stays dry in wet weather. Minimum creepage distances are 20 to 25 mm (kV), but must be increased in high pollution or airborne sea salt areas. Types of insulators. These are the common classes of insulator. Pin-type insulator. As the name suggests, the pin-type insulator is mounted on a pin on the cross-arm on the pole. There is a groove on the upper end of the insulator. The conductor passes through this groove and is tied to the insulator with an annealed wire of the same material as the conductor. Pin-type insulators are used for transmission and distribution of communications and electric power at voltages up to 33 kV. Beyond operating voltage of 33 kV, the pin-type insulators become too bulky and hence uneconomical. Suspension insulator. For voltages greater than 33 kV, it is a usual practice to use suspension-type insulators, consisting of a number of glass or porcelain discs connected in series by metal links in the form of a string. The conductor is suspended at the bottom end of this string while the top end is secured to the cross-arm of the tower. The number of disc units used depends on the voltage. Strain insulator. A dead end or anchor pole or tower is used where a straight section of line ends, or angles off in another direction. These poles must withstand the lateral tension of the long straight section of wire. In order to support this lateral load, strain insulators are used. For low voltage lines, shackle insulators are used as strain insulators. However, for high-voltage transmission lines, strings of cap and pin insulators are used, attached to the cross-arm in a horizontal direction. When the tension load in lines is exceedingly high, such as at long river spans, two or more strings are used in parallel. Shackle insulator. In early days, the shackle insulators were used as strain insulators, but nowadays, they are frequently used for low-voltage distribution lines. Such insulators can be used either in a horizontal position or in a vertical position. They can be directly fixed to the pole with a bolt or to the cross-arm. Bushing enables one or several conductors to pass through a partition such as a wall or a tank, and insulates the conductors from it. Line post insulator. Station post insulator. Cut-out cap and pin insulators. Higher voltage transmission lines usually use modular cap and pin insulator designs. The advantage of this design is that insulator strings with different breakdown voltages, for use with different line voltages, can be constructed by using different numbers of the basic units. Also, if one of the insulator units in the string breaks, it can be replaced without discarding the entire string. Each unit is constructed of a ceramic or glass disc with a metal cap and pin cemented to opposite sides. In order to make defective units obvious, glass units are designed with Class B construction. so that an overvoltage causes a puncture arc through the glass instead of a flashover. The glass is heat-treated so it shatters, making the damaged unit visible. However, the mechanical strength of the unit is unchanged, so the insulator string stays together. Standard disc insulator units are 25 cm in diameter and 15 cm long, can support a load of 80 to 120 kN, have a dry flashover voltage of about 72 kV, and are rated at an operating voltage of 10 to 12 kV. However, the flashover voltage of a string is less than the sum of its component discs, because the electric field is not distributed evenly across the string, but is strongest at the disc nearest to the conductor, which flashes over first. Metal grading rings are sometimes added around the disc at the high voltage end, to reduce the electric field across that disc and improve flashover voltage. In very high voltage lines, the insulator may be surrounded by corona rings. These typically consist of toruses of aluminium or copper tubing attached to the line. They are designed to reduce the electric field at the point where the insulator is attached to the line, to prevent corona discharge, which results in power losses. History: the first electrical systems to make use of insulators were telegraph lines. Direct attachment of wires to wooden poles was found to give very poor results, especially during damp weather. The first glass insulators used in large quantities had an unthreaded pinhole. These pieces of glass were positioned on a tapered wooden pin, vertically extending upwards from the pole's crossarm. Natural contraction and expansion of the wires tied to these threadless insulators resulted in insulators unseating from their pins, requiring manual reseating. Amongst the first to produce ceramic insulators were companies in the United Kingdom, with Stiff and Dalton using stoneware from the mid-1840s. Joseph Bourne producing them from around 1860 and Bullis from 1868. Utility patent number 48906 was granted to Louis A. Covert on 25 July 1865 for a process to produce insulators with a threaded pinhole. Pin-type insulators still have threaded pinholes. The invention of suspension-type insulators made high-voltage power transmission possible. Pin-type insulators were unsatisfactory over about 60,000 volts. A large variety of telephone, telegraph and power insulators have been made. Some people collect them, both for their historic interest and for the aesthetic quality of many insulator designs and finishes. One collectors organization is the U.S. National Insulator Association, which has over 9,000 members. Insulation of antennas. Often a broadcasting radio antenna is built as a mast radiator, which means that the entire mast structure is energized with high voltage and must be insulated from the ground. Steer-tight mountings are used. They have to withstand not only the voltage of the mast radiator to ground, which can reach values up to 400 kV at some antennas, but also the weight of the mast construction and dynamic forces. Arcing horns and lightning arresters are necessary because lightning strikes to the mast are common. Guy wires supporting antenna masts usually have strain insulators inserted in the cable run, to keep the high voltages on the antenna from short-circuiting to ground or creating a shock hazard. Often guy cables have several insulators placed to break up the cable into lengths. Unwanted electrical resonances in the guy. These insulators are usually ceramic and cylindrical or egg-shaped. This construction has the advantage that the ceramic is under compression rather than tension, so it can withstand greater load, and that if the insulator breaks, the cable ends are still linked. These insulators also have to be equipped with over-voltage protection equipment. For the dimensions of the guy insulation, static charges on guys have to be considered. At high masts these can be much higher than the voltage caused by the transmitter, requiring guys divided by insulators in multiple sections on the highest masts. In this case, guys which are grounded at the anchor basements via a coil, or if possible, directly, are the better choice. Feed lines attaching antennas to radio equipment, particularly twin-lead type, often must be kept at a distance from metal structures. The insulated supports used for this purpose are called standoff insulators.